Okay, so this is another part of the fundamental theorem of calculus. So this is actually so important, in fact, that most books you look at, including like the Princeton Review, refer to this as the second fundamental theorem of calculus. So the first one, the integral from a to b of f of x dx is f of b minus f of a. This is referred to as the second fundamental theorem of calculus. And all this says is that if we have an integral of some continuous function, and we can find the derivative of that integral, and more specifically, the derivative of the integral is the function itself. Okay, so really this is just really making it very clear that the derivative and the integral are inverse operations. Now, because of the chain rule, if this right here is a function in terms of x, then what we're going to have to do is we get the function itself with g of x, and then we have to multiply by the derivative of g of x. So we'll do an example, then I'll show why this works the way it does, and then just take it from there. Okay, so first example, h of x equals the integral from 4 to 5x of sine of t dt. Find h prime of x. So h prime of x equals, which notice h prime of x is the derivative of the integral. According to this rule, what we're going to do is we're going to have f of t, so we have a function in terms of t. The derivative of the integral is f of g of x. So in this case, g of x is 5x. So we will have sine of 5x times the derivative of g. In this case, g is 5x, the derivative of g is 5. So why does this work this way? Well, let's say I've got the integral from 4 to 5x of sine of t dt. Okay, so let's just integrate this using the fundamental theorem. So the integral of sine of t would be negative cosine of t. And this is from 4 to 5x. And so the fundamental theorem of calculus says we go ahead and plug in. We get negative cosine of 5x minus negative cosine of 4. Okay. But remember, we're not actually integrating this. We're finding the derivative of the integral. So if I find the derivative of this, all right? Well, the derivative of negative cosine is positive sine times the derivative of the inside, so that's times 5. And then this guy right here is a constant, so the derivative of a constant is 0. And so here we go, which is what we have. So the second fundamental theorem of calculus here, again, it's just reiterating that the derivative of the integral is the function, that they're inverse operations. So look at the next example, we're finding the derivative of the integral. Okay, so we have a function in terms of t. So this is going to equal 1 over the square root. And all we're going to do is we're going to substitute in for t. We plug g of x, which is secant squared, in for t. So we get secant to the 4th of x minus 7 times the derivative of g. Now the derivative of secant squared, we have to use the chain rule. So this is like u squared. The derivative of u squared would be 2u, so we have 2 secant of x, times the derivative of u, which would be secant x tan x. All right, so we've got 2u times u prime. And so we can just rewrite this as one term. We've got 2 secant squared x tan x over the square root of secant to the 4th x minus 7. Question on these first two examples. And believe it or not, it is this straightforward. This is the one, probably the one theorem that, besides the extreme value theorem, that a whole lot of people are like freaked out about. Because here we've been doing this really complex stuff for a while, and it's like, I'm just replacing a t with this other thing. Yeah, basically. We're replacing the t with our function, and the only thing you got to remember is multiply by the derivative of that function. Okay? Now, there's a couple of little things. For example, what if the bounds here were reversed? So what if on my example here, what if instead of going from 4 to 5x, it was from 5x to 4? Right? Think about how that would change things. Well, instead of this being 5x and 4, right? Instead of this being 5x, this would be 4, and this would be 5x. All right, so how would that change? Well, the derivative of this would be 0 minus the derivative of this. So we would have a negative in front, okay? Which fits in with the rule that we saw, and you're going to want to write this down. Recall that the rule, if we have the integral from a to b of f of x dx, that's equal to the negative of the integral from b to a of f of x dx. If we flip the bounds, we reverse the a and the b, we change the sign of the actual integral. Okay? And that applies for this. So if instead of a to g of x, it were g of x to a, you would flip the bounds and throw a negative out in front. Okay? And then you follow the same process. The next example, same idea, but now the bounds, instead of just being a constant to a function, now it's a function to a function. Now both these functions are in terms of x, and the function we're integrating is in terms of t. So it follows a very similar rule, but now it's more similar to the fundamental theorem of calculus. Remember, if h were a constant, h prime would be 0. So this wouldn't be here, which is why the first one is there. But if h isn't a constant, if h is actually a function, we have to take h into account. And so we have f of g of x times g prime of x minus f of h of x times h prime of x. So essentially we plug in the top, multiply by the derivative of it, minus, plug in the bottom, multiply by the derivative of it. Okay, so let's do this example really quick. So q prime of x equals, now notice where the t is, that's e to the t, that's the only variable in this expression, right? If we had a whole bunch of variables, we'd replace every single t with x squared. That's the only t, so we have tangent of e to the x squared, and we multiply that by the derivative of x squared, which is 2x, minus, same idea, we plug in 2 to the x to the t, so we have tangent of e to the 2x times the derivative of 2x, which is 2. That's the derivative of that integral. And so notice again, this only applies when we're doing the derivative of the integral. This isn't changing anything we've done before now. Okay, we're not suddenly doing some weird new magic with integrals. We still integrate the same way. This happens to be we're finding the derivative of the integral, and that's what we get. Okay? Questions or concerns on these three examples? Yeah, so that's our final. You could factor out a 2, right? They have a common 2, but other than that, there's really nothing else you can do. So yeah, this would be it. So there are a few problems, 11-ish, 12 problems. All practicing this for the most part. Notice we got the derivative of the integral, right? So that's the common thread today, derivative of the integral. We'll have a quiz tomorrow over definite integrals. We won't include this. And yeah, just the rest of the period to work on.